Inviscid limits for the stochastic Navier-Stokes equations and related questions.
Okay. Well, first of all, thanks to IMPA, and a especially big thanks to Milton and Helena, who have been fantastic hosts here, even nursed me back to health after getting sick last week. I want to talk today about some results for statistically invariant states for some nonlinear SPDEs coming from fluids, mainly around the 2D Navier-Stokes equations and some related equations. I think there's always this sort of gut-wrenching discussion we have whenever we talk about stochastic Navier-Stokes. Why is one adding noise to these systems? So I wanted to start with some general background in turbulence, which I think gives one, sort of good and systematic answer to the question. I will say there's been some really nice remarks by various speakers this week, so apologies for a little bit of a repetition and on some things about turbulence I'm sure many of you guys know better than I do, but nevertheless, I think it gives good motivation for the results that come. And then I want to talk about a unique ergodicity result for the stochastic Boussinesq equations with a particular forcing structure. We'll talk about some results on inviscid limits in the class of invariant measures then for the stochastic Navier-Stokes equations, which gives us some ideas about a certain class of inviscid measures for the Euler equations. And then talk about some work on a fractionally dissipative stochastic Euler equation, along with some work on shell models that are activated by white noise forcing. So it goes without saying you don't need to be an expert on fluids to realize that for many questions around turbulence, the best you're going to do is try to predict universal, maybe statistical features. And I think it goes back to Richardson, this idea that you should try to understand how energy, according to some average, is meted out between different spatial and temporal scales in the fluid. And he has, I think, the first empirical law about minus 5/3, how turbulence is partitioned between different spatial scales. But Kolmogorov in 1941, through dimensional analysis, was able to sort of derive this law. And subject to all kinds of caveats, we really do observe this stuff in the real world. So here's this familiar picture. I'll just point out a few things. Vince just put this up on his slides. So we have this energy cascade in the inertial range, which is independent in this range of the kinematic viscosity. We derived this K41 theory essentially from dimensional analysis. You assume that the energy spectrum is just a function of this dissipation anomaly and the wave number, and just matching up units, you get this k to the minus 5/3. You get a smallest scale of motion. And so we believe that we get this picture sort of independent of how we're stirring the fluid at large scales. We just care that it's sort of frequency localized, so we're only injecting energy at the largest scales of motion. And again, this picture is purely statistical, so we need to make some good sense about how this is actually tied to the equations. Of course, I think everybody in the room well knows that deriving this picture in any way from the actual equations of motion is a big, outstanding open problem. A lot of what I'll say about 2D a lot of what I'll say today is about 2D. So this is the theory of Bachler and Crichton in particular. Here we assume, instead of an anomalous dissipation of energy, which you wouldn't expect given all the conserved quantities in 2D Navier-Stokes, that you have an anomalous dissipation of entropy. Okay. And so we have another picture like this. This being the, you assume that there's this anomalous dissipation of entropy. You match up units, and you get this k to the minus 3. You integrate forward and you realize there's some energy missing from the system. And so based on that, you sort of, their deep insight is that you have this backwards cascade. And I'll just note that, again, we have the similar question of actually connecting this picture to the equations. Huge open problem. And also, in order to have this backwards cascade represent some sort of statistically stationary state, we need some sense of a sink at the largest scales of motion. So just some pictures. We see, I think, quite a different behavior between the two-dimensional and the three-dimensional flows. I think this is actually a simulation based on 3D stochastic Navier-Stokes equations. But in any case, you see these sort of large-scale structures in two-dimensional flow and this sort of more uniformly, I guess, turbulent behavior, for lack of a better word. Okay, so what challenges does this bring from the point of view of the governing equations? Well, first of all, we'd like to identify some universal statistical features. So this is very much in the program of the deterministic as in the stochastic situation. Namely, you'd like to show that there's a unique statistically invariant state of the equations, or at least some observables that observables against that statistically invariant state would be the same. We'd always get the same, let's say, k to the minus 5/3 law out of the equations. But more important than it be unique, it's that it be observable. So Vince, actually, in recent talk, I think several people at this conference have introduced this generalized Banach limit. You'd like to know that the actual measurements, some sort of time averages, are the same as what you'd get measuring against these statistically invariant measures. And even a step more ambitious is to try to verify various ansatz of turbulence. So, for example, the dissipation anomaly of, or anomalous dissipation of energy in 3D or entropy in 2D. So I think, as Idris adroitly pointed out, one of the main advantages of the stochastic versions of these equations is that you can actually have some hope of verifying these sort of ergodic hypotheses here for these sort of systems. And I'll try to elucidate at a little bit more of a technical level why this is. But just given this idea that we get this cascade regardless of the exact structure of the way energy is being put in at the injection scale, this idea that we would use a white noise and time-driven forcing as sort of a proxy for genericity in forcing. And this goes back to Novikov in the 1960s, and is really a major way in which one injects energy into these systems in numerical and in theoretical point of view. So I'd like to elucidate some ways in which we've made maybe a little bit more progress on these questions in a stochastic framework. Okay, so just to put this in some general mathematical terms, we'll be thinking of a stochastic PDE like this. And we'd like to study this system within a Markovian framework. So the Markov semigroup evolves forward observables of the system. In this manner, I run forward solutions in many sample paths, take an observation, take a statistical average, and that's my Markov semigroup. The dual semigroup is used. The dual semigroup, fixed point of the dual semigroup represents a statistically invariant state. But in simpler language, the dual semigroup represents, evolves forward probability distribution functions, starting from some initial probability distribution. And an invariant measure would be a set of initial conditions for which, if I look at the probability distribution function at any forward time, you get the same probability distribution. Okay, so we have the mathematical goal of characterizing the existence, uniqueness, and I would say attraction properties of these statistically invariant states. Okay, so the existence is just an easy exercise. It's the Krylov-Bugliov procedure and applies just as well for a deterministic version of these equations. It's really the uniqueness that's the grand challenge, as I have been alluding to. Okay, so why do we have a better hope of getting uniqueness in the stochastic setting? Well, corresponding to the, we can describe the dynamics of the Markov semigroup in terms of a partial differential equation. This is the so-called Kolmogorov equation. And so here it is. And so really, from a sort of probabilistic point of view, we'd like to verify two things in terms of getting uniqueness of the invariant measure. One is that we'd like to show that this Markov semigroup has some smoothing properties. This is sort of natural that you'd assume that the dual of this actual this PDE invariant measures would be represented by fixed points of this system. So if we have some nice smoothing properties, we're going to hope that we have better uniqueness results. And then we'd like that there's an irreducibility condition, that there's a common state always reached by the dynamics. So going back to some work in the mid-90s by Flandoli and Maslovsky and a number of authors afterwards, there's been a kind of program of trying to, based on this sort of starting point, try to understand in which situations, in terms of the driving noise, we can obtain uniqueness for this system. Now, as we started with, we only want to inject noise at some specific scales, right? So this means that this problem, which we want to show as smoothing, is very hypoelliptic. So we're talking now about really about Hörmander's theory going back to the 1960s, where we'd like to understand we'd like to be able to show that a bracket condition is satisfied. In this work, in this famous work of Hörmander, he showed that for basically partial differential equations of this form, if I form a sequence of brackets in this way, Lie brackets, that if I can span the phase space through successive brackets, then indeed I have many of the smoothing properties that I would expect of, say, the heat equation from this degenerate situation. Okay, but in infinite dimensions, okay, we're dealing with a partial differential equation on Hilbert space. So this is quite a difficult object to be working with. So among these various works, there was a very nice breakthrough work of Eyre and Mattingly in recent years, 2006, through some important follow-up works in the last few years, where essentially they began to develop a theory of hypoellipticity for infinite dimensional systems. So they had sort of two insights. One is that you didn't need as strong a form of a smoothing for the Markov semigroup as maybe the classical theory would ask for in order to have what you need to get a unique invariant measure. So they introduced this so-called asymptotic Strong-Feller condition, which is quite topological, but at the level of gradient estimates on the Markov semigroup, it's saying that I can estimate this observable in terms of this, the gradient of the Markov semigroup of this observable in terms of the observable itself, supremum of this observable, and something dying off in the gradient of the observable. And then they showed that working with some sort of infinite dimensional analog of the Hörmander bracket condition, one could show that this would be enough to get this sort of weaker estimate on the Markov semigroup. So, of course, doing any of this requires a detailed understanding of the interaction between the nonlinear and stochastic terms in the equation. So I think this is also kind of an exciting direction in that it's really, you really want to understand how the Navier-Stokes nonlinearity and the forcing interact in order to produce this sort of unique invariant measure and these sort of results. So we wanted to understand how far this sort of new technology could be taken. So with some colleagues, we decided we would look at the a version of the Boussinesq equations with some excitation only through this sort of temperature equation. Just exciting, let's say, 4 Fourier modes. This is maybe, we chose this example as for sort of illustrative purposes, but I'll make a few remarks about what sort of stochastic forcing regimes would be admissible for these sort of results, and see when we could produce a unique ergodicity result. I have Charlie here in the audience, so I should mention that still we're dealing with a case where we have periodic boundary conditions, and we have no net temperature differential in this system. So we can't expect that there's some dissipative structure in here and still hope for an invariant measure. We'd like to handle a more physically relevant situation, but I think just as a exploration of the dynamics of this bracketology, this question was interesting for us. Okay, so future work on a more physical situation, but first the theorem. So we proved that if you force just 4 Fourier modes in the temperature, the 4 lowest modes, that you have a unique invariant, ergodic invariant measure, and that it has some very nice, strong attraction properties. So it's mixing in the sense that if I evolve forward an observable, take some average, that at a fixed time, this is going to be close, exponentially close, to that observable against the unique invariant measure. So this observable really would represent, 2-point correlation functions in the fluid, or you probably want to measure particular Fourier modes, things like that. Also, if you're willing to trade your average over many runs for a long average over time, you also get this almost sure, we call this a law of large numbers, a strong law of large numbers for this sort of system. Okay. So let's try to understand what the bracket structure of this system is. So we start by activating some modes in the, let me say this. So we start by activating some modes in the temperature equation. And after taking a bracket, we see that we've activated some modes in the equation for vorticity. I've written this in the vorticity form. Okay, but along with some stuff downstairs here is activated directly by this direct forcing through this bracket. So we have a term that looks like this. Something we want to begin to fill the phase space plus something that seems quite undesirable a priori. Very complicated structure. Okay, now let me see. So then we would like to, so basically every mode we have downstairs, we have some roughly corresponding mode upstairs. And so we'd like to use this guy to now generate more modes downstairs. Okay, so we'll bracket again this guy with the full nonlinearity of the equation. Okay, so that's going to give me something that looks like part of the advective derivative term. So that's good. And so then if I bracket again with this guy, then I get something that looks like another direction sort of downstairs. And I can iterate this process around and gradually fill up the phase space. So we're using the fact that we, from the nonlinearity of this system, that if I have, so I'll write something like theta. So if I do sigma k, sigma j, I have something of the order of sigma k plus j, which is just trigonometry. Okay. Our classical Hörmander condition would imply that all we need to do is fill up the phase space with this union. But somehow, since we have infinitely many dimensions to get into, for noise to sort of leak into, we need to complement the fact that we're filling up the phase space with what's going on at small scale. So the idea is somehow to couple the use of this Hörmander condition with Fourier Prodi-type results. Well, in the earlier works of Eyre and Mattingly, they have that they can exactly fill up the phase space, okay, without any errors leaking into the highest parts of the Fourier spectrum. And for us, whenever we fill up a piece of the phase space, we get these error terms that interact in the wrong ways. So in fact, how many brackets we have to take for us depends on the individual sample paths of the solution. And the number of brackets we're taking depends on this in a sort of bad way. So we had to sort of rework the analysis of the actual usages of the Hörmander theory in order to analyze this system. So aside from the fact that this led us to some interesting study of the dynamics, I think, for this model, we had to sort of rework what it meant to be satisfying this Hörmander condition in an infinite dimensional setting. Okay, so just a word or two about what's involved with this on the technical level. The insight is that if you want to be generalizing results on hypoellipticity to infinite dimensions, one could take the route of analyzing the degenerate parabolic equations directly. That seems to be out of reach. On the other hand, from the probabilistic point of view, since there's such a strong connection between degenerate parabolic equations and stochastic evolution equations, a subject called Maliovan calculus was developed to give a probabilistic proof of smoothing for these type of parabolic equations. And it turns out that this route via Maliovan calculus is a good route for generalization in infinite dimensions. So one way to see this Maliovan calculus is through this machinery, a stochastic integration by parts formula. We're actually able to translate this gradient estimate on the Markov semigroup, on the evolution semigroup for these equations, into a control problem. And it's solving the control problem through use of an object, which is really the Gramian matrix, that one proves the smoothing estimate. And it's understanding the spectrum of this Gramian matrix that we're actually making use of at the analytical level, the fact that we've got a good bracket condition satisfied. Okay. All right. Now for something somewhat different, or starting using maybe this sort of technology as a starting point, we'd like to see what happens in this class of invariant measures for a simpler system now, the 2D Navier-Stokes equations on the torus I've written in vorticity formulation. We'd like to know what happens in this class of measures as we take nu to 0. Okay. So, given that Euler somehow is the most relevant equation for understanding a lot of turbulent behavior, we expect that if we can get an Inviscid measure, it should contain good statistics of 2D turbulence. However, as we'll see, in this for the 2D Navier-Stokes equations, we don't get an anomalous dissipation of entropy. So one should well expect that this is maybe not quite the right setting for turbulence. But this may not be so surprising as we don't have a damping at the largest scales or any mechanism to destroy the energy coming back. Okay, so I'll come back to this point. But anyway, this is the question. We'd like to know what the correct scaling is between the kinematic viscosity and the coefficient in front of the noise as we take this thing small so that this class of measures is tight. When do I go until I'm not? I just want to calibrate myself. Anyone? what's my...
Till 5:05.
5:05. This is accurate?
Yeah.
Okay. So let's see. So if we write down these equations and we take the scaling alpha as square root of nu, just some basic things with Ito lemma, and using the fact that we have 2 and many more conserved quantities in the equations, we've got 2 quantities that are bounded independently of nu. And so this is enough to show these guys are tight. In fact, one can go further and show that any other scaling, if I, let's see, if I add too little noise, so I put a high power of gamma, I get either a Dirac, so just my invariant measure is the zero solution of Euler, not very interesting. Or if I put any even a little bit too much noise, this thing doesn't even have any convergent subsequences. So for this 2D Navier-Stokes equations, this is the only scaling that works. So this observation goes to Kuchsen, and in a series of works, he studied this class of invariant measures, showed they were tight based on this simple observation, and then produced some other very interesting properties, including that these Inviscid measures were non-trivial, that they had interesting, that they weren't supported simply on points. But he ends up with a measure that's supported on solutions of the free Euler equation, but with this rather strange-looking phase space that looks more appropriate, actually, for strong solutions of 2D Navier-Stokes than Euler. And the natural question that Vladimir Šverak asked us last year at the IMA is, shouldn't these invariant measures be supported on L infinity of vorticity, which is a natural space for 2D Euler? Why? Well, I'm insulting many intelligences in the audience, but we have all the conserved quantities here, including an up to L infinity, and based on this beautiful result of Udovich that's been mentioned several times during this conference, this is a good space for well-posedness. And going a little further, one can see that this actually gives us a nice phase space to study the long-term behavior if we equip this L infinity with weak star topology. So this gives us a setting in which we can really try to connect what's inside of these measures to what would be going on in the long-term behavior of 2D Euler, and to try to see, in any sense, whether there's some sort of interesting stochastic annealing process that's going on in this particular Inviscid limit. So we were indeed able to show with Vladimir and Vlad that we could obtain a uniform bound on this class of measures in the L infinity of vorticity topology, and thus obtain that the Inviscid measure, the Kuchsen measure, is supported on L infinity even with some moments. Okay, so this involved an iteration procedure for stochastic drift diffusion equations that we think has some independent interest. But first, let me talk about some consequences, or some postulates that we can make about the structure of this measure based on having the measure supported on this space. So we have for Euler these infinitely many conserved quantities. We call them Casimirs. Okay, and so if we, starting from an initial condition, capture all of the Casimirs associated with a particular initial condition in a set like this, then we know that the long-term behavior of Euler in this topology, the omega limit set, is contained in the weak star, L infinity weak star closure of this set. So what one can make postulates about what, in fact, is sitting inside of these omega limit sets. So this is the statistical mechanics view of 2D Euler. One would hope to fix a notion of entropy and maximize or minimize, depending on your sign, maximize the entropy, subject to the constraints in the system within the weak star closure of this set. Okay, so there are different ways you can fix entropy. There's a whole literature on this. But in the wash, what you get is some sort of nonlinear Poisson problem. And solutions of this nonlinear Poisson problem will give you a conjecture about what's in the omega limit set of 2D Euler in the weak star limit. Let's note that many of these Casimirs can drop on end states. So we would expect in this minimization procedure that, in fact, these statistical mechanics view would produce quite simple elements in the long-term behavior of Euler. This is, however, the statistical mechanics view doesn't have rigorous proof and is an outstanding problem for Euler. And in fact, we don't have a single example of a trajectory which is not weakly compact, which is not pre-compact in L2. So this gives us sort of two extreme scenarios that we can consider. One is that the invariant measures consists of entropy maximizers. And there's some nice recent work of actually two of my collaborators, Foldis and Schwerak, to say that if you have a reasonably small initial energy and some reasonable conditions that your notion of entropy is strictly concave, then all of these entropy maximizers are really simple flows. On the other hand, we can't rule out that some of the orbits are pre-compact in L2, which would lead to more complicated dynamics. And one can consider that the answer may be somewhere in between. But this does give some evidence that these measures are actually picking out some relatively simple behavior. Okay, so in order to establish this estimate, we needed some sort of uniform bound. And in the end, we realized we could prove something stronger, which was some sort of instantaneous regularization, going from any L2 initial condition. Okay, so maybe I should explain the relation here. If I take our stochastic equation here, not had a good relationship with these lines here. Okay, so, and then I rescale. What I get is that rescale time, what I get is an equation of this form. Okay? So we want to be able to prove that for a velocity drift which is smooth, but nothing else, we're going to assume stochastic forcing, say, is only on certain scales or with a fast enough decay that for any value of viscosity I have smooth solutions, but nothing else about A, right? This is acting as a 1 over nu. I forgot a tilde here. That we have some sort of instantaneous regularization, that going from basically L2 in space initial conditions, instantly I'm in L infinity. Okay, so this involved developing a Moser iteration scheme for stochastic PDEs. And I'll note here, too, that this provides an effective way of dealing with fractional order dissipations for this system, really any order. If one's trying to naively estimate this thing with just LP Ito lemma, if one didn't have these stochastic terms, if this was just a deterministic forcing, one would almost immediately get L infinity bounds by taking p to infinity. But one gets this sort of bad power of p from the Ito correction term. So in developing this iteration scheme, we're trading basically some integrability in time, right, for higher integrability in space using basically the dissipation and some interpolation. You'll notice I'm using this sort of anisotropic scaling in space and time, and this is in dealing with these stochastic terms. But when we take pth roots of all of this, this square power of p is going to be rendered harmless. And in addition, we're going to get some nice regularity improvement results out of this system. So one ends up with this balance. One needs to estimate stochastic terms. So we come to my favorite Martingale inequality, the BDG inequality. We have to be a bit careful about constants here. But in the end, we get a nice Moser iteration scheme in these expected values. And, okay, well, we need to rescale back time. But since we have basically invariance, which we're going to be using in the end in passing to a limit, this is enough, indeed, to get the L infinity results we desired. So a lot of open questions remain around this business. First of all, we sort of believe, and around this first conjecture that the omega limit sets would actually contain just laminar solutions, we sort of believe that this measure should be supported on smoother solutions. But we're very essentially making use of the exact cancellation, the divergence-free condition in this setup. So we believe that, have a maybe fairly strong belief that there should be better regularity, but that remains an open problem. We also, just in general, would like to understand better the long-term, what's sitting inside of this support. Is it just constant solutions? Could there be somehow periodic orbits and that sort of thing? Although that seems to be an even harder thing to get one's hands on with current technology. And maybe one doesn't expect that these guys are unique. Okay, so I mentioned that there's no anomalous dissipation of entropy. And this is maybe quite to be expected. You'd like to add a large-scale damping to the system. And in fact, maybe the most effective thing to produce the Batchelor-Kreiknon cascade, or what you would believe would do this, would be just add a damping at the frequency localized to the largest scales. And in fact, if you add a zero-order damping, Constantine Ramos and some other recent work of Basaya Ferrario proved that you have, in fact, no anomalous dissipation of entropy. So instead, we'd like to, consider frequency localized damping or some sort of negative order damping. So this was more conceptual than, I would say, deep at the level of functional analysis or something. But we wanted to demonstrate that, in fact, if you add a damping term, even a very weak damping term, mainly concentrated at the largest scales, then this breaks this scaling that Kuchsen observed. And in fact, it's quite the opposite. You have an order 1 noise at the level of the Inviscid limit. Okay. So, namely that if you have any decrease in the order of the noise as nu goes to 0, you just converge to a Dirac measure, and so on. Okay, so, yes? No, that's the point. I want to, you would think that what would be your dissipation mechanism at the largest scales as you take viscosity to 0? I sort of imagine that you, so my ideal, okay, so mathematically, I am able to prove QED that if I add a 0th order damping, but I keep it, okay. Physically, I believe, but I can't prove this yet, that if I just have this be frequency local, and I don't think I know how to prove it, but I think if I just frequency localize this and just have a damping, let's say at the largest wave numbers, and I keep that fixed, but I take the Inviscid limit, then this class of measures should remain tight, even in that case. Yeah. So, I mean, so you might expect in some other situation that the energy introduced at the intermediate scales would have further and further to go, but all of this that I'm discussing is on the periodic box. So unless we have some mechanism like that, then I don't expect. Yeah. Yes? Yes. Existence and uniqueness of just solutions, or ah. No, but let me interject and say. Okay, you're actually introducing my. Let me answer you by saying I don't know, but you're touching on the next point actually, which is this solution that I get in the limit is just a Martingale solution. I'm not making any claims about uniqueness. Yeah, no, it's a fair question, but just so that I'm checking myself that we didn't prove something that's not true. This solution that you get in the Inviscid limit. It's not in any way a unique solution. It's just a Martingale solution. And in fact, what's undesirable about this result as it stands so far is I just have that the resulting Inviscid equation is stationary. I don't have any attraction properties here. So with Peter, actually, we started to ask, at just at the level of damped Euler, could we recover the Hörmander type results when we have a zeroth order damping? So here, the sort of desirable phase space one would like to work with in terms of the existing technology would be L2 of omega, something like that. But there we only have weak solutions. We don't have uniqueness. Maybe we could work in the Udovich setting. This is zeroth order damping now that I'm discussing, where there everything should be fine. But then we're working with L infinity with weak star topology. It's not even a Polish space, and we have a quite undesirable situation to work with. So, so one has well-posedness in higher order Sobolev norms as well, but there in HR you don't even know if you should expect any decay in those norms. So we decided to punt on this question for a later day and ask simply what would be the smallest order of dissipation one could add and still obtain a unique ergodic invariant measure for this system. So what we were able to, in fact, prove is that with any order of fractional dissipation, okay, we could obtain a suitable gradient bound on the Markov semigroup in the HR topology, and hence conclude that this system possesses a unique ergodic invariant measure. But since we're forced to work in this higher order Sobolev space in order that we have a nice topology to work with these equations, existence, uniqueness, continuous dependence on data, and the pathwise sense, we needed to find a way to make use of the parabolic smoothing beyond the fact that it directly induces decay in the phase space. And at a sort of technical level, this sort of analysis deeply depends on having moments, or at many, many points in the analysis we're using significantly that we have moments on the solution, namely exponential moments on the solution. And due to a lack of cancellation, having exponential moments in the HR topology is completely out of reach and maybe shouldn't even be true. But we have some exponential moments in a weaker topology than is the phase space, something like L2 or LP of vorticity, and even L2 of velocity. And so based on that, we're able to, in fact, show that we can obtain these sort of gradient estimates on this guy. And in particular, bootstrap up not exponential moments, but at least polynomial moments in these higher order spaces using some sort of smoothing arguments. Okay, so let me just, do I have 2 or 3 more minutes? 2 more minutes? Let me conclude. There's been a lot of talk here this week also about shell models. So given that we have such a complicated wave number dependence in the equations, if we simplify the model, this probably being the mother model, we might be able to obtain results that we wouldn't ever pray to obtain in a lifetime for the full 3D system, but for this simplified model. So a lot of people have been working on this model. There are a lot of different shell models. I say this is maybe legitimately the mother model because this was one of the first shell models and one of the simplest. Right? We've got the Gouy model and Saber model, which have quite a bit more complicated wave number dependence. But this was sort of the simplest and original model for shell models. And so we were able to, in this simplified setting recently, show that, in fact, we have a dissipation anomaly, or an anomalous dissipation of energy and a dissipation anomaly in this system of equations in the vanishing viscosity limit. So this is certainly an expression of the fact we can get a better handle on the direction of the cascade for such a simpler setting. One thing that I think is interesting about these that sort of was highlighted for me in looking at this problem, when looking at we're able to show at positive viscosities that these invariant measures corresponding to this equation are unique, and we make use of this in establishing this dissipation anomaly here. And there we again have to study the sort of bracketology of these equations. It turns out that when studying Navier-Stokes, one is directly using basically a bracket of B against a already obtained direction, and then bracketing against one of the originally forced direction in order to get a new direction. So you're really using long-range wave number interactions in studying the Hörmander bracket condition for stochastic PDEs, or so far in what's studied for stochastic PDEs. And indeed, we use such long-range interactions for looking at this stochastic Boussinesq equation. Here, in fact, we only have local wave number interactions. And this actually quite complicated our analysis of establishing hypoellipticity. So there are still many things to be understood in this sort of setting. All right, so just to conclude, or maybe I should quit. Well, thank you all for your attention.